Section 14.2, Euler Circuits and Route Planning. The 7 Bridges of Königsberg. In the early 1700s, Königsberg was the capital of East Prussia. Königsberg was later renamed Kaliningrad and is now in Russia. The Pregel River runs through the city and branches into 2 rivers with an island labeled A in the middle as shown. The problem asks us, is it possible for a citizen to take a stroll through the city, crossing each bridge exactly once, and beginning and ending at the same place? Simplify the problem by drawing a graph whose vertices represent the 4 land masses and whose edges represent the bridges connecting them. Then try to find a circuit that uses each edge exactly once. So we're going to draw the map as a graph. Set up your vertices with B, C, A, and D. From B to A, there is 1 bridge. From B to C, there is 1 bridge. And from B to D, there is 1 bridge. From A to D, there are 2 bridges. And from C to A, there are also 2 bridges. We want to try and find a circuit that uses each edge exactly once. We want to use each edge. So let's talk about it. B, C, A, D, B. If I go B, C, A, D, B, that doesn't use these 2. So it doesn't work. Try again. If we go B, C, A, D, B, A, C, B, B to C, C to A to D, D to B, B to A to C, and back to B. But it uses B to C and C to B again. There are other circuits we could also try. Reviewing some vocabulary. A path is a walk that uses each edge only once. A circuit is a path that begins and ends at the same vertex. An Euler path is a path that uses every edge of the graph exactly once. And an Euler circuit is a circuit that uses every edge exactly once. A circuit starts and ends at the same spot, at the same vertex. A path does not start and always end at the same spot. So here we go. Consider example 1. Look at the graph. We've got vertices E, F, D, A, B, and C. And our first question is A, B, C, D, E, F, A an Euler circuit? Here we go. Trace it. A, B, C, C to D, D to E, E to F, F to A. Is it an Euler circuit? No, because it does not use F to D, F to B, or B to D. It does not use each of the edges. Can you find an Euler circuit? I'm going to start at A, B, C, D, E, F. Gets me around this way. I want to use the inside stuff now, so I'm going to go D, B, F, and back to A. I used each edge only once. Yes, I found an Euler circuit. Euler's theorem says that in any connected graph, if the graph has an Euler circuit, then each vertex of the graph has an even degree. If each vertex of the graph has an even degree, then the graph has an Euler circuit. Example 2. What does Euler's theorem tell us for the 7 bridges problem? If we look here at vertex D, there are 3 edges coming from it. It is degree 3. Vertex A is degree 5. C is also degree 3, and B is degree 3. Our degree of our vertices are odd. Euler's theorem tells us it has to have an even degree. So we know that there is not an Euler circuit for the 7 bridges problem. Example 3, decide which of the following graphs have an Euler circuit. Looking at graph A, the one that looks like a pinwheel, I'm going to start down here at G, vertex G, and it's degree 2. H is degree 4. I is 4. J is 2. K is 4. L is 4. A, degree 2. B, degree 4. C, degree 4. D, degree 2. E, degree 4. And F, degree 4. All of those vertices have an even degree, so yes, there is an Euler circuit. If we look at graph B, right here at vertex D, we can see it's degree 3. It's odd, so no, there is not an Euler circuit for graph B. Example 4. Can you draw the following graph without lifting your pencil and without redrawing any of its edges? We're going to trace it with no redrawing, so we're asking if there is an Euler circuit. Check the vertices. This vertex right here is degree 3, which is odd, so no, we cannot draw it without lifting our pencil and without redrawing any of its edges. There is not an Euler circuit in this graph. When we want to find Euler circuits, we have to talk about cut edges. A cut edge in a graph is an edge whose removal disconnects a component of the graph. Example 5 says to identify all cut edges in the graph below. Okay. Look at the edges of the graph. Are there any we could take away that would split our graph into 2 different pieces? Sure is. If we take away D to E, we then have this A, B, C, D part of the graph, and we have E, F, G, H. D to E is the only cut edge in this graph. To find Euler circuits, we're going to use Fleury's algorithm. It's written in your notes for you. Don't get overwhelmed by it. We're going to use cut edges, okay? Start at any vertex and choose any edge from the vertex. Go along your edge and remove it from the graph. You're now at a vertex on a new graph. If the only edge is a cut edge, use it. Then remove it. Otherwise, choose any edge that is not a cut edge. Go along the edge and remove this edge. Repeat step 2 until all edges have been used and you've returned to the vertex from which you started. Write down the letters of your path as you go. It will make more sense as we do an example together. Example 6. Use Fleury's algorithm to find an Euler circuit in the following graph. Here's our graph. Notice we don't have vertex A on our graph. It starts with vertex B. The first thing we're going to do is we're going to start at vertex C and go to D and remove that edge. So far our path is C to D. We went from C to D and removed that edge. Now looking at D, we can go from D to E, D to F, or D to G. And we're going to go from D to G. So our new path now is C to D to G. From G, we'll go to F. Our path now is C, D, G, F. From F, our only option is to go to D. So our path goes C, D, G, F, D. And now F is all by itself over here. We now have a cut graph. If we follow our path that we're left with, we can now go D to E, to G, to H, to B, to C. Oops. We can trace it around, starting at D. Let's check if it's an Euler circuit. C to D, D to G, G to F, D, E, G, H, B, C. Yes, it's an Euler circuit. Talking about Euler paths. Euler paths have 2 odd vertices or 0 odd vertices. A graph with an Euler path that is not an Euler circuit has 2 vertices of odd degree. An Euler path that is not an Euler circuit starts at one vertex of odd degree and ends at the other vertex of odd degree. So it's a path that uses each edge only once. We might have Euler path. When we do have Euler paths, we need vertices of odd degrees. That's section 14.2, Euler circuits.